Welcome. We're going to talk about projectile motion today and go over some projectile motion concepts and then some projectile motion problems in which we'll engage in problem solving, but then also cover concepts. But first I want to go over a problem that was on the quiz, a vector addition problem. And I had a couple people ask me about it, how to do it, and then one person made a specific request to go over it. You will all have different numbers. This just happened to be the set of numbers that popped up when I looked at this. But it was Jack Sparrow was on a boat, and the wind blew him due east for 14 kilometers. And then the wind switched directions and blew him 9 kilometers at an angle 9 degrees north of east. And then he fell asleep. When he woke up, he noticed the wind was blowing him 15 degrees south of east. And to his surprise, after 22 kilometers, he was back on the island from whence he started. So how far did he go, and at what angle did the wind blow him at night? So one person, in fact, asked, how did this happen? Is this magic? And I actually wondered that first. How could he be going east, 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 and then at the end still be going east, yet end up back? First I thought maybe he went around the world. But no, I realized that at night he drifted back this way, or someone took him back this way, and then ended up at home. He ended up at home. So I noticed I didn't mark the directions here. And I won't actually do east because I'm going to be drawing some vectors there. So first we've got 14 kilometers. And this time I remembered to put a protractor here. I can't move it around. I still need to figure out how to move objects around because once I upload the template, it's static, it's frozen. But I can use a ruler. So 14 kilometers, we need some sort of a scale. Now I could go 14 centimeters, so 1 kilometer is 1 centimeter, but that would get pretty long. My ruler isn't that long. I truncated it. And also, even if I did have a full-length ruler, 22 centimeters is pretty long. So let's just say that 1 centimeter, let's put this in red. So 1 centimeter scale, oops. It's pretty bad when you can't spell scale without missing a letter. Equals 2 kilometers in real life. So our first one is going to be, so 14 kilometers, that's going to be 7, oops, I don't want to do that, I want to use this here. So seven centimeters. And these are not going to be super precise. So first I'm going to just make a sketch, and then we'll do it analytically. The next one, 9 kilometers at 9 degrees north of east. I realized after I uploaded this, I should have put my ruler under the protractor. So I'm just going to kind of guess. So 9 kilometers in real life is going to be 4.5 centimeters. I'll just sort of guess at the 9-degree angle. That's not a great 9-degree angle, but it's okay. So here we had 14 kilometers. Here we have 9 kilometers. And now goes to sleep and ends up somewhere over here goes 22 kilometers and ends up back at the island. We can make the island, we'll have it a lush green island here with Keira Knightley and Orlando Bloom. So whatever attractive person type you prefer, they're both there. Okay, so we could draw this vector over here, but we know that when we draw a vector, as long as it has the same length and the same direction, I should have actually chosen arrow instead of a line. If it has the same length and the same direction, it can be any old place. So 22 kilometers, that's going to be 11 centimeters on here. And it's at 15 degrees south of east. So it's going to angle down like that. So we'll move that over here. Because we know, and I'm not sure if I can push it. Oh yeah, okay. So this is really what it looks like because he ends up off the screen. Let me move my little templates over here. He ends up off the screen, but it really helps us visualize it if it is over here instead. And this one is 22 kilometers. That doesn't look very good. So our resultant vector is going to, let's do it this one instead. So we want to know how far and at what angle did the wind blow him at night. So how far it blew is right there. So this is the resultant vector. And what we need to do then is find the components of that. So our plan find X and Y components. Each vector. So that's 1, 2. We're going to then add X components together and add Y components together. And then we'll use trigonometry to find R, because we know R is going to equal the square root of Rx squared plus Ry squared. And then also to find the angle theta. And what this tells us here is it gives us approximately the length. And if I could actually move my ruler, I could drag this over and measure the length. What you should do, though, you do have a movable ruler in your hand, or you can access one. You should do this drawing here, use your scale, measure this out, and come up with a certain number of centimeters. And if you came up with say 25 centimeters for this purple resultant vector, 25 centimeters is equal to 50 kilometers in real life. So with a ruler, you can determine pretty close your displacement, and then you can use your protractor and figure out what this angle is. Let's just label that with a little hash. You can figure this angle here as well. We're going to do it analytically, but I like also doing it graphically as well. Even if you aren't super precise, you can get something that's close, and then you can check yourself as well. Let's go to the next page here. I've got my notes. Oh, and let's go back, and let's just call this vector A. This is vector B, and this is vector C. So Rx equals AX plus BX plus CX. So AX is just simply 14 kilometers. There is no Y component. So that's 14 kilometers. BX is 9 kilometers, and it's at 9 degrees north of east, and the X component is along where the angle is located. So let's just quickly draw that one. So here's B, and there's theta. So we've got, this is B sub X, this is B sub Y. So this is going to be 9 kilometers times the cosine of, just for some reason, 9 degrees. Yeah, in my notes, I've got my notes here, but I wrote the wrong numbers down, which wasn't very smart, because I have in my notes a different number. Cosine of 9 degrees plus 22 kilometers times the cosine of 15 degrees. Oops, wrong way. R sub y is going to be the same thing. That's going to be AY plus BY plus CY. And now there's no component of Y, or no Y component of A, so that one's going to be 0. For this one, the Y component points upward. So we've got plus 9 kilometers sine of 9 degrees. And notice the 14, I'm sorry, the 22 kilometers, that actually points downward. So for that component, we're actually going to subtract off 22 kilometers times the sine of 15 degrees. And I'm not going to add these up. You can do that, but you're going to get something that is quite long here in the X direction. You're going to get this. It's going to be R sub X. And You don't necessarily know it because we haven't figured out the numbers, but it's going to match the drawing. Notice that the y vector is a net downward pointing below the axis. So this is going to be r sub y. And it's going to be a very small number. In fact, it's going to be smaller than what I have shown there. That's going to be r. So we can find r that way. And theta is going to be the inverse tangent of opposite, so ry over rx. And we're going to get a certain number of degrees. It's going to be a small number. I forget, it's going to be about 6 degrees south of east. So folks that are watching, I don't know if you have any questions about this one. The most likely place to make a mistake, there are a lot of places where you could make a mistake. I would say the most likely place to make a mistake is on this right here, where you add the y component for the 9 kilometers, but then you subtract off the y component for the 22 kilometers. And in fact, when I was helping someone with this, they added both of them, and I took a quick look at it and said, oh, yeah, that looks good. But then when I went back over it later, I realized, oh, I think I gave that person some wrong advice. So this is probably the place where most people are going to make their mistake. So now on to projectile motion. So one of the main points here of projectile motion, so is that the x and the y components of motion are independent of each other. So if I toss a ball and it follows some sort of a downward path like that, it initially has some sort of a velocity in the x direction. And if I throw it straight out like this, its initial velocity in the y direction is 0 because I'm not throwing it up, I'm not throwing it down, even at an angle, I'm throwing it straight out. So in this case, there is an acceleration in the y direction. Equals negative g. There is no acceleration in the x direction. So Vx initial equals Vx always. So this equation here applies. So we can find the x direction if we know the initial velocity, for example, and we'll do a couple sample problems. So for this case here, we do have an acceleration. So we can basically use the y version of this equation here. Y equals y0 plus v y0t plus 1/2 ay t squared. So notice in one of these, actually let's do the same thing here. X equals x0 plus vx0t plus 1/2 ax t squared, but that equals 0. So we use the same equation in both directions. The same equation describes the position change in both directions. It's just that in the x direction, the acceleration term goes to 0. So this equation and this equation are the same if acceleration is equal to 0. So another thing that's important is the projectile takes a certain amount of time to fall. That value of t is the same in both equations. So this t and this t are the same. So the t term in the x and the y equations are the same. So for example, you could solve the x equation for t and plug that value into the y equation. So that essentially gives you more parameters to use to solve the problem, or any sort of projectile motion problem. Let's just look at what I said here conceptually, because I drew a quick sketch, obviously not a superbly drawn sketch. This is something that looks a little bit better. So here's a ball that's been projected upward. Maybe a soccer ball that's been kicked, or a ball that has been thrown. And let's notice what we have here. So this is a ball that's been tossed up at an angle. So I've got a ball in my drawer. So it's just my squishy moon ball here. You can see the craters on there. So this is a ball that I have tossed up at an angle like that. Well, I haven't tossed it. Look at me giving myself credit. I did toss this one, but I didn't necessarily toss that one. So if you notice, as the ball is moving upwards, it's getting slower and slower, and that sort of makes sense. You know that if you throw a ball up, if I throw it straight up in the air, you can see it's at its fastest when it leaves my hand, and it comes to rest for one moment at the top, and then it speeds up again. So the same sort of thing if I were to do this, and it's such a short distance, it's really difficult for you to tell as I'm tossing the ball to myself on camera. It's really difficult to tell, but it is moving at its slowest up here. And then when it gets back down to my hand level again, it's moving fast. If I were to let it go and not catch it, it would be moving even faster down below that level. If you were to break down how the velocities change over time, because there's no acceleration in the x direction, the x velocity does not change. So acceleration means changing velocity, or it actually means changing a velocity over time ratio. So if you do not have a changing velocity, then you don't have acceleration. So this vector here, the blue one, stays the same length all the time, and it shows it better right here. If you look at what happens to the y velocity, sort of this orangish vector, initially you're tossing it and it's going upward. But since there's an acceleration that's downward, the velocity is going to be getting smaller as you go upward. So if this was, so this is 0, let's just say this is situation 1 here. So notice that V0y is greater than V1. So acceleration equals delta V over delta T. So that equals, generically, V final minus V initial over delta T. In this case, V final is V1. V initial is V initial y, and that's over delta T. And since V1 is smaller than V2, this is going to be a number that is less than 0. And that makes sense because this is negative g. Let's call this situation 2, this situation 3, 4, 5. So if we look at V3 and V4, all right, let's go V3 and V5. It's a more noticeable difference. So V5 is longer than V3, but V5 is a negative number, a big negative number. V3 is a little negative number. So if we look at, so this is A for this case right here. Let's look at another example. So this is A 0 to 1. Let's look at A 3 to 5. So that's going to be V5 minus V3 over delta T. So V5 is a big negative number. V3 is a little negative number. So because of that, we're going to have a big negative number minus a smaller negative number that's going to still be a net negative. So on the way down, the acceleration is less than 0. So let's look at V2 and V3. So let's just say that these were taken just before the top and just after the top. So let's say that the magnitude of V2 equals the magnitude of V3. So A23 is going to equal V3 minus V2 over delta T. So the magnitudes equal each other, but V3, and let's just define them to equal to V. So in this case, V3 is negative V. V2 is V, so that's minus V over delta T. So that also is going to be less than 0. So even as it's turning from going upward to going downward, we still have the acceleration less than 0. So notice for the y vectors, they are biggest the farther below the peak you are. As they get up towards the peak, the y vectors get to be 0. As you go back down again, the y vectors increase. And at all times, the actual overall velocity is the vector sum of x and y. So that's going to get longer. So as time goes by, and let's v increases, and points more and more in the y direction. After the ball or the object reaches its peak. So that's just a qualitative look at that, how the velocity changes. So some key things here. So key points. Vx is constant. Ax equals 0. And ay equals negative g. So these two accelerations don't influence each other at all. And that's what I meant back here when I say the x and the y components of the motion are independent of each other. All right, so let's solve a problem. An eagle is flying horizontally at a speed of 3 meters per second when the fish in her talons wiggles loose and falls into the lake 5 meters below. Calculate the velocity of the fish relative to the water when it hits the water. So let's start off with the drawing. So we've got our bird, and it's carrying the fish. Fish isn't looking too happy. All right, and then the bird lets go of the ball. It says it wiggles loose and falls into the lake. So because the bird is flying, so it's flying horizontally at a speed of 3 meters per second. So V0 equals 3.00 meters per second horizontally. So because the bird is flying that way, that means the fish has an initial velocity of 3 meters per second. Oops. We're going to go with the traditional XY number line here. All right, so this thing is going to let go. And if you remember from what I said a little bit ago, Vx is constant, Vy, this time we don't have an up motion, just a down motion, so Vy is going to be continually increasing in the downward direction. So we're going to get something that looks like that. Here's our water. So it's going to have a final velocity here as well. That's going to be a larger arrow than this one. So if we look at this, we know V0 is 3 meters per second. That's V0x and V0, which equals. So we want to calculate V final. So we want V, and so we don't know what the x component is. We don't know what the y component is. We don't know what this angle is. So, is what I have there accurate so far? Things we don't know. Well, again, we said that the velocity in the x direction doesn't change. So I said we don't know V0, or we don't know Vx. We do know Vx. That's going to be (3 meters per second). So now with our coordinate system, we have y. Let's see how I did it here. Yeah, so y0. The lake is 5 meters below, which means the fish is 5 meters above the lake. We can say we measure from where it's dropped, so x0 equals 0. Doesn't matter what time of day this is, so we can just have the clock start at 0. We also know that x equals 0, or that's what we're going to assume. And what that really means is we're assuming no significant air resistance. And we know that AX was 0, AY is negative G. So over here, we don't know T. We don't know X either. But this is really our target, this value and this value. Because remember, to define velocity, we need a magnitude and a direction. So we already know Vx. We need to know Vy. So we can go back and figure out what that is. So if we look at these equations right here, we know acceleration. We know the change in position in the y direction. And we know what the initial y velocity is. So we know that Vy0 equals 0. So it looks like the best one to use is that equation right there. So Vy squared is Vy initial squared plus 2Ay delta y. That's equal to 0. So we can just plug in. It's going to equal the square root of 2Ay delta y, which equals the square root of 2 times negative 9.8 meters per second squared times delta y, which is y final. That is 0. So y final is 0. Oops, that's not a 0. 0 minus y initial, which is 5 meters. So we've got a negative here, we've got a negative here. We don't end up with a negative inside the square root, which is a good thing. And that comes out to be 9.9 meters per second. But we need to remember that when we do this, it can be either positive or negative 9.9, because 9.9 squared is going to equal this number under the radical, but so is negative 9.9 squared. So we need a negative sign because the velocity is downward. So to figure this out then, we go, so V is equal to the square root of Vx squared plus Vy squared, which is the square root of 3 meters per second, quantity squared. And even though some of these things seem kind of obvious, I would not leave steps out when I solve these things. I like to show as much work as possible. And we've got the negative 9.9 in here, but when we square it, that's going to become positive. So that comes out to be 10.3 meters per second. So it started at 3 meters per second, it ended at 10.3 meters per second. And all that gain is because of the increase in velocity due to the downward pull. So even though the velocity didn't change in the horizontal direction, it did change in the downward direction. So theta equals the inverse tangent. So here's theta, there is v, and we have an x component and a y component. Negative 9.9 over 3 equals negative 73 degrees. So V is equal to 10.3 meters per second at 73 degrees below the horizontal. We could also use this, I'm out of space though on this page, we could also use this to find x, so how far forward did the fish fall, because it was continuing to go forward, and then also how long did it take to hit the water. So this is now problem 28 in our book. A daredevil is attempting to jump his motorcycle over a line of buses parked end to end by driving up a 32-degree ramp at a speed of 40 meters per second. How many buses can he clear if the top of the takeoff ramp is the same height as the bus stops and they are 20 meters long? And then we can discuss our answer. So the motorcycle takes off at this angle here, theta. That's V0, and then it ends up, oh, let's try. So maybe the buses are out on a grassy knoll or something like that. It's probably some of the worst bus drawings I've ever seen. And then it lands over here. So V0, (40 meters per second), theta equals 32 degrees. And now we need to choose our ruler. So it doesn't really matter. It ends up at the same height that it takes off at. So x0 equals 0. y0 equals 0. Doesn't matter what time of day we do this. So we'll have t0 equaling 0 as well. So if we break this down into components, this is V0x, and this is V0y. So we can break this down into components also, the velocity into components. So V0x equals 40 times the cosine of 32 degrees. V0y equals 40 times the sine of 32 degrees. And then over here, when we go to the final, since it ends at the same level as it starts at, V is also going to equal 40 meters per second. Same theta. That's pretty ugly. X equals, we don't know. Y equals 0. T equals, we don't know. And we know that V final X is 40 times the cosine of 32 degrees. And we know that V final Y is going to equal negative 40 times the sine of 32 degrees. Because initially the Y vector is pointing up, but then on the way down, the Y vector is pointing down. All right, so we want to know how many buses can it clear. So how many buses means we need to find X. So this is our target variable. So if we go back to our equations here, I will start with the simplest one. So X equals X0 plus V times T. Well, we don't know T, but there's no other equation that's really going to help us either, because you could say, well, let's use this one. We don't know X, we do know acceleration, except the problem with this one is, if we're looking for X, yeah, we don't know X, but the acceleration in the X direction is 0, so that actually zeroes this term out. And this just is a way to kind of pseudo-derive that V final and V initial in the X direction equal each other. So we're going to use this equation right here, which just comes from the definition of velocity. All right, well, X0 is equal to 0. So here we don't know X, and we don't know T. So that's one equation, two unknowns. But remember that because the X and the Y are independent of each other, we can find T from a Y equation. And plug it in. So if we go back, so we know Vy initially, we know Vy finally, we know the acceleration in the Y direction, so we can use this equation here to find T. So Vy equals V0y plus AYT. Oh, and of course, we already have talked about AX equals 0. AY equals negative G. So if we solve this for T, so T equals Vy minus V0y over A sub y, and now we can plug this in. This equation. So X equals V0x, that's just from right here, times T, which is Vy minus V0y over A sub y. And we'll go back to, we're going to go to this work page here. I should have left myself an extra little page at the bottom. So that means that X equals, and I'm just going to plug in the numbers, 40 times the cosine of 32 degrees. Vy was, so that's the final, so Vy is let's go with this here. So Vy final is negative. So negative 40 times the sine of 32 degrees minus 40 times the sine of 32 degrees divided by negative 9.8. And this is 40 meters per second. That's meters per second as well. When we plug all this stuff in, we come out with 147 meters, which is not a very good looking abbreviation for meters. So does this answer the question? And no, it doesn't directly. We still need to know the number of buses. So the number of buses is going to equal X, which we found, divided by the bus length. So that's 147 meters divided by 20 meters per bus. So the meters cancel, the per bus moves up to the top, and we get 7.4 buses. And we know we can't have 0.4 buses, so that means it can jump the motorcycle or the motorcycle and rider. The extra 4/10 of a bus is margin of error. Because it asks about that. It says, discuss what your answer implies about the margin of error in this act. That is, consider how much greater the range is than the horizontal distance he must travel, to miss the end of the last bus. Yeah, so he will land well onto the end of the ramp. And usually daredevils, they don't want to overshoot too much. They don't want to overshoot the ramp. They want to actually land on the ramp. So 4/10 of a bus, 20 meters, that's about 8 meters. So the ramp is probably more than 8 meters long, so things work out. All right, that's projectile motion. Just to quickly review, the kinematics equations are the same for projectile motion. Key points for projectile motion: x velocity stays constant, the y velocity changes by this acceleration factor, -g. The velocity, as if something falls, the velocity increases because lost my cursor there. The velocity increases because the y velocity is increasing. And notice that we're using formulas that we're familiar with. So these are all formulas that came from the last chapter. We've seen this formula before. We've seen this formula before. In fact, this bottom one just comes from the definition of acceleration. So you'll notice I didn't use the range equation. The book lists an equation. They call it the range equation. That only works under very specific parameters. So I like using the generic equations that are always correct for constant acceleration, things like the two that I've underlined. So folks that are watching, any questions? I don't see any in the chat room or the chat space. All right, so none for the moment. Sounds good. I will stop the recording, and we'll see you, or you'll see me. Well, you'll see me the next time you actually watch this. And I'll see you when we have our test, and maybe I'll see some of you virtually as well. All right, talk to you later.